First speaker this afternoon, it's Eric Daub, who's a principal data scientist in the research engineering group at the Alan Turing Institute. And he will talk about a software library for uncertainty quantification using Gaussian process emulators. Thank you, Eric.
Okay, thanks, Simon. Can everyone hear me okay?
We hear you, sure. Go ahead.
Wonderful. Okay, so Serge invited me to give this talk, to talk a little bit about a software library that myself and a few other members of our team at the research engineering group at the Turing have been working on. I should also mention, in addition to wearing an RSC hat in this, I'm also a computational physicist by training who's worked a lot on earthquakes. And so I certainly appreciate the challenges on this general UQ problem from a domain practitioner's standpoint. So I think it's a really interesting, challenging, multidisciplinary problem. And I'm hoping, from my perspective now as a research software engineer, that software can really help illuminate some of the challenges and address these by creating useful tools that can address a wide range of problems. So just this is part of a project, and Serge is one of the PIs that is attempting to create a useful software library to do uncertainty quantification for complex physics simulators. These are typical, multi-scale, multi-physics problems. And our hope is that by creating a robust and well-engineered software library, we can carry these out. And the main thing I'm going to talk about today, so this project has been going on for a little more than a year and a half now, but there has been a pause since the pandemic started in March. And so today I'll be talking a bit about some work that I did on this at the beginning of this calendar year in really beefing up and improving the Gaussian process emulator that's central to this approach. And then beyond my efforts to create the software library, we have a number of collaborators that are applying these to applications such as climate modeling, tsunami simulations, and myself have done a bit of work in this area using earthquake simulations. We really are trying to test this out on a number of different domain areas to see how we can use these tools effectively to understand a wide range of physical problems. So just a bit of background on what we're trying to do. We're trying to do a UQ workflow, and in particular, this is an inverse or calibration problem. So the idea is that we have some simulator and some data and some general vague idea of parameter space that are going to be the inputs to the simulator. And what we'd like to know is an inverse question. Given the data that we have, what are some relevant input values that we can use from the parameter space that tells us how the simulator might be used for making predictions about the real world? So this is the idea: is we have some data, and then we have a simulator, and then given some choice of parameters, we can determine which of those are sensible for our problem. And the problem with the simulator is it's usually very expensive to run, and it's usually very nonlinear. It may have a large partial differential equation you have to solve or something like that, such that you can't just do this directly, where you query this parameter space many, many times and then compare the output of the simulation with the data. So a common approach in these types of problems is instead to use a surrogate modeling approach. And to kind of break this down a little bit, you have sort of three components that you need to sit in the middle of this to carry this out. So from your parameter space, you need a way to pick samples of points that you'd like to run through your simulator. And you can choose this in any number of different ways. We have a number of different ways that we've implemented this in our library. I'll just talk about some simple ones today because I'd like to focus a bit more about some of the challenges in building the surrogate model. What that is, it is an approximate, cheaper model that you use to approximate the simulator based on a number of discrete samples that you've taken from your experimental design. So once you do that and you fit some cheaper computational alternative to your simulator, then the idea is that you redraw points from your experimental design, but in a much denser fashion, such that you can run those through your surrogate model and then compare that to your data in ways that you can then estimate what plausible inputs are. Now, the main approach that we've been taking in our initial implementation in this library is known as history matching, where the idea is you'd like to rule out different parameters you think are implausible given the data that you have and all the uncertainties involved in this calculation. But there's a number of approaches you might also take alternatively to doing this history matching. But today I wanted to talk a little bit more about the ways that we can improve some of these surrogate modeling approaches. We've seen some talks today talking a bit more about Gaussian process emulators, but just to re-show kind of this classic illustration of this, we have a number of discrete function evaluations of some complicated function, and we'd like to do a regression approach that then gives us some approximation to the underlying function. Part of the reasons that Gaussian processes are very popular for this type of uncertainty quantification is it's relatively straightforward to compute some uncertainty estimate because if we want to quantify uncertainty, we need to know how accurate our surrogate model is. So given a number of data points, the Gaussian process gives you a straightforward way to fit some model that can then be queried cheaply at any number of points. Typically, we calculate some mean function out of the posterior mean from this Gaussian process, which is our best estimate of the output of our simulator at some arbitrary point. Then you can easily calculate some error bounds. And as you can see in this typical example, we have some nice smooth interpolation between these known points. And as you get further away, you become a little bit more uncertain about the value. But the nice thing about Gaussian process is it's fairly flexible in that it will do a good job of interpolating between these with a function that's as complicated as it needs to be in order to fit all of these. In more classic machine learning approaches, you often spend a lot of time specifying the exact functional form that you might want for this in order to get a good fit. And there's things like trading off between overfitting and underfitting, bias and variance in your model. And those things are very robustly handled by Gaussian processes. So that's why it's often very nice for this type of problem. However, one thing that we sort of gets lost in these simple pictures right here is that in complex simulators, you usually have a much higher dimensional space than this. And it's usually much more expensive to draw samples than kind of this typical sampling density you might see in one of these things. So this is often not really the picture that you're going to have when you are trying to apply this to some complex simulator. And back at the start of this project, one thing that we looked a lot into was the fact that different software libraries often will assume sort of the simplest form of this Gaussian process. It'll assume there's a zero mean. It'll assume certain things about the covariance structure in this, because usually this is applied in like a machine learning standpoint where you have lots of different samples, and you're assuming that you want to be minimally prescriptive about the form of this, so that your data really drives the form that your approximate model takes in this case. But that's often very much not the case when you're doing UQ, and you need to do something a bit more sophisticated in setting up these Gaussian processes. So just as a motivating example, this is actually something I've taken from the documentation and the examples we have in our software library. This is a pretty simple problem. It's a projectile with gravity and drag. And the idea is, if we don't know a couple things about this problem, say this drag coefficient or the initial velocities at which this projectile was fired, we can then integrate this ODE system and figure out where this projectile lands some distance later. So we'll explore this problem a little bit more. But the thing I'd like to do with this is, because this is a relatively cheap simulator to run, but it has some of the nonlinear aspects we might expect of a more complicated simulation, is what happens when we actually sample this relatively sparsely. So here I have just a design with 6 different points. So here is my parameter space. I have the velocity at which I shoot the projectile on one axis, the drag coefficient on a log scale on the other. And I've drawn some sample points in here, and then I've actually calculated for a large number of samples what the true simulator looks like. And as you expect, as the launch velocity goes up, this projectile goes further. As the drag coefficient goes up, the projectile doesn't go as far, and there's some nice shape to this. And if you were just to take these 6 points and just take an out-of-the-box implementation of a Gaussian process using something like maximum likelihood to estimate some of the hyperparameters, which are the things that describe sort of the shape that you expect of this covariance structure to take for this type of model, this thing falls over completely flat. Basically, it says, I assume that there's a zero mean, and these sample points just are basically something that says this is just noise around the zero mean. So every time that I would try to query this at some unknown point, it would just tell me that the projectile is just going to go 0, and it's not particularly very useful. And that's just because we don't have enough information with just these sample points in order to create an effective emulator for this type of problem. However, we do have some, because this is a physical problem, we do have some contextual information, some idea of what we might think, some of the shape of this simulator function might be. But it's often very difficult to sort of codify that in different problems without, good software implementation of this. So one thing I've spent a lot of time doing is implementing flexible mean functions, which you can use to kind of say, okay, here's the approximate shape I expect my model to take. It helps with interpretability and things like that. And one thing that R users might be familiar with is the string style formulas in R. And we've been writing this in Python. We wanted to have an implementation that captures a lot of the nice flexibility of that. So in our library, if you just pass a string to this mean function object, it will automatically do a certain number of expansions. So in R style formulas, this one variable times another means all linear combination, both the linear term of x2 and x3 plus the product of that. So if you just sort of look at one of these mean functions, it automatically adds like some constant on this. It has this quadratic term that I want, plus some of these other terms that I have. And so it automatically constructs these for us and can use that in fitting this model. So now if I go ahead and you use a linear mean function, and the other thing that I can do is I can put priors on some of these hyperparameters. This is something that's not often implemented in a lot of machine learning libraries. And that's just because you often are just not trying to specify a lot of prior information you have about your function. You just want the data to speak for itself. And what this does is, even with only a few sample points, it makes it so you actually have something that's somewhat useful. So with our mean and prior information on some of these hyperparameters, we actually get something that at least is somewhat useful. I will admit this isn't perfect, but I didn't spend a lot of time, thinking about what my mean function might look like, or what some of the prior information that I might expect to put on some of these hyperparameters. So even though this is still poorly sampled, this is a lot better, and with a bit of effort and some cross-validation, you might be able to really help this. And the other thing that's nice about these Gaussian processes, it will actually tell you, I'm really uncertain about the value of this function in particular places, so that you can, if you can draw more samples, where you might want to concentrate those, or whether or not this emulator is any good. I think this is certainly, we're making good progress on using this and actually applying this to real problems. And I think this is sort of filling a void that certainly I found in looking at lots of software implementations for this, to do this GP fitting really well, so that you have something that's robust and can be used in a number of different applications. Just in case people are wondering, the code to recreate some of these examples is now part of the library and on our documentation. Here's some websites you can go to on GitHub, as well as the documentation on Read the Docs. And then this third link is to actually show on the documentation page some of the code I used to create this example. So please do feel free to take a look at this, get in touch with me if you're interested in using this or find this useful, have any questions. I'd certainly be happy to collaborate and try and make this, this tool useful to lots of people. So appreciate your attention, and I'm happy to answer any questions.
Thanks a lot, Eric. I don't see any questions at the moment in the chat.
Yeah, I'll keep an eye on the chat, and if any of those pop up, I'd be happy to answer in the chat.
Sure. I think in the interest of keeping to time, we'll go to the next talk, and then maybe in the panel session we can come back to these things.
Yeah, great.
So thanks very much, Eric.
Thank you.
So